So today I'm going to start reactions of organometallic compounds, and the first reaction is oxidative addition. Now, before discussing oxidative addition, let's spend 1 minute on what is oxidation, what does it means, what happens in the oxidation. When there is oxidation of any species, we say that some species is going to oxidize. In that case, what happens actually? In that case, actually, the electrons are released from that species, which is going to be oxidized. And we know when the electrons are released from a species, then there is the increase in the plus oxidation state of that species. So in the similar way, something happens in this oxidative addition reaction. What happens in the oxidative addition reaction? That species which is going to be oxidized is a metal here. Now, what happens here in this oxidative addition reaction? We'll discuss taking an example. Let's say we have this some complex LNM, and it is reacting with XY, that is the ligand. So when this undergoes oxidative addition reaction, what happens here? This bond which is between XY and Y, it breaks, and this is the bond formation between metal and this ligand X, and metal and this second atom of the ligand Y, and there is the transfer of electron from metal to the sigma antibonding molecular orbitals of this XY, groups of this XY ligand. So what happens here? This type of complex forms. Okay, so the bond between X and Y, the sigma bond is breaking in this case, and bond between metal and this X atom of this ligand, metal, and the Y atom of this ligand is forming by back donation of electrons from metal to the sigma antibonding molecular orbitals of these XY ligands. If you see here, in this process, since electrons are going from metal to the ligand, that means metal will undergo oxidation, and there is the increase of +2 oxidation state. That is, the oxidation state of metal is increasing by +2. If here the oxidation state is N, here it will be N plus 2. Okay? This is the oxidation state. If here is N, here will be N plus 2. Also, the coordination number of this ligand is increasing by +2. If the coordination number here is Cn, then the coordination number in this complex will be Cn plus 2. Along with this, that the electronic count of complex is also increasing by +2 in this case. Okay, if here is electron count is EC, which is electronic count, here it will be EC plus 2. Why there is the increase of +2 in electron count? Because one electron is coming from this X, another electron is coming from this Y. Okay, so in this oxidative addition reaction, what is happening here? The oxidation state of metal is increasing by +2, the coordination number of the complex is increasing by +2, and the electron count of the complex is also increasing by +2. Okay, now there are few features, you can say rules by which we can find out whether a reaction or whether a complex will undergo oxidative addition reaction or it will not undergo. Now, the first case or the first rule is that the metal should be in low oxidation state. Metal should be in low oxidation state. That is, either it should be in +0 or +1, or sometimes plus to oxidation state. Okay. Second point is that this complex which is undergoing this oxidative addition reaction, it should have at least 2 vacant site on which the coming ligand can attach. Okay, that means the complex should be unsaturated with respect to the coordination number. Third one, if the metal in the complex has d0 electronic configuration, then there will be no oxidative addition reaction will take place, because if metal has d0 electron, then this increase in +2 oxidation state will not take place. Therefore, the metal should not have d0 electron configuration. There should be some electron in the metal. Okay. Also, number 4, the rate of oxidative addition increases if some sigma donor ligand is coordinated to the metal. Now why this? Because the sigma donor ligand will increase the electron density of the metal, and when the electron density of the metal will increase, it will give electrons easily to the ligands, and hence the rate of the reaction will increase. Okay. Next is number 5. Next point is that the presence of pi acceptor ligand, if attached to the metal, it decreases rate of oxidative addition. Okay. Next point is that the rate of oxidative addition reaction decreases with increase in oxidation state of metal. That means metal should be in lower oxidation state. Okay. Now next point is, that is very important point. Now when we move in the periodic table from top to bottom, okay, top to bottom in periodic table, okay, then the rate of oxidative addition increases. Then oxidative addition rate increases. For example, let's say we have iron in zero oxidative state, we have ruthenium in zero oxidation state, we have osmium in zero oxidation state. This belongs to the 3D series, this belongs to the 4D series, and this belongs to the 5D series. Now we know that when we move from 3D to 4D, 4D to 5D, the electronic cloud around that nucleus increases. That means the force of attraction between the nucleus and the outermost electron, which is present in the outermost shell, it will be very less, and therefore that electron can be easily donated to a ligand. So therefore, as we move from iron to osmium, the rate of the reaction, that is oxidative addition, increases. Here, this will be the rate of reaction for that oxidative addition reaction. Also, when we move left to right in periodic table, okay, the rate of oxidative addition decreases. Again, let's take an example, then I will explain why this is happening. Let's say we have iron in G-oxidant state, we have cobalt in +1, and we have nickel in +2 oxidant state. All have D8 electronic configuration. Now, in this case, the rate of oxidative addition follow this trend. And this trend is again related to the size of this metal. We know that when we move from left to right in a periodic table, the size of metals or atoms decreases. Now, when the size decreases, the force of attraction between the nucleus and the outermost electron, that increases, and more is the force of attraction, more difficult is the donation of the electron, and hence lesser is the rate of oxidative addition reaction. Okay, so these are the few points that you must remember while you are going to study or going to do the practice for this oxidative addition reactions. Okay, now next let's see the nature of these X and Y ligands. That what is the class of this X and Y ligand, whether they are polar, non-polar, or anything else. Okay, now this ligand X and Y, ligand X and Y, it can be a polar ligand. It can be a polar ligand. Okay, for example, it can be HX, where X is equal to your chlorine, bromine, and iodine. It can be any alkyl halide or some acyl chloride, etc. This XY ligand, it can be non-polar. It can be a non-polar species or ligand. Non-polar, for example, H2, Cl2, O2, some alkane, or this can be your silyl hydride or tin hydride. These are your these non-polar ligands. Or it can be a ligand which has multiple bonds, okay, and during which the bond between X and Y is retained. ठीक है, ligands in which the bond, I see this is number 1, number 2, see this is number 3, bond between X and Y retained. This also can be this type. For example, if you see oxygen, or if you see this keto compound, or your alkene, acetylene, etc. Here, since in the oxidative addition there is the breakage of only one sigma bond, then another bond will be remain intact in the molecule. Okay, so X and Y can be like this, a polar molecule, it can be non-polar molecule, or it can be a ligand in which the bond between and XY is retained. Okay, now let's see the mechanism or possible pathways by which the oxidative addition reaction can take place. That is the pathway or mechanism mechanism of oxidative addition reaction. Oxidative addition reaction. The first mechanism is concerted mechanism. Concerted mechanism. Now, what is the meaning of this concerted mechanism? What does it means? Concerted mechanism means it's a type of mechanism of or reaction in which the bond breaking and the bond forming process occurs simultaneously. Okay, and this concerted mechanism is given by any complex when this X and Y is a non-polar ligand. X and Y is a non-polar ligand. ठीक? For example, it is H2, Cl2 or O2. Okay. Now, what happens in this concerted mechanism when this metal complex is reacted with this X and Y ligand? First, there is the formation of sigma complex. Sigma complex by the coordination of this X and Y ligand with metal through a sigma bond, and then the bond between X and Y breaks, and the bond between metal and X and metal and Y forms by the back donation of electrons from metal to the sigma antibonding molecular orbital of the ligands. Okay. Now let's see one or two example for this concentrated mechanism. The first example that I am taking is the reaction of Voska complex. This is the Voska complex. It is iridium complex. Okay. Iridium and Cl pH3 CO pH3. This is Voska's complex. When this Voska complex is reacted with H2, first there is the formation of sigma complex between this Voska complex and hydrogen through the sigma bond between hydrogen and iridium Cl pH3 pH3 and CO, and after this bond breaks and there is the bond formation between iridium and these hydrogens. Okay, then there is a bond formation between hydrogen and iridium. Okay, this type of complex will form. In the same way, we can see another example. Now this time we can take some different molecule. Again, let's see. I am taking again this Voska complex, iridium, then PPH3 here, then Cl, CO, PPH3, and this time I am treating it with some alkene molecule. Okay, when it's treated with the alkene, first there is the formation of sigma complex. This type of sigma complex will form between this Voska complex and this ethene molecule. And then breakage of sigma bond or one bond between carbon and carbon of ethene. And what happens in this case? C, H2, H2. One bond between alkene breaks and one remain intact with the carbon. Okay. So it Cl, PPH3, CO, PPH3, and you will get a metallocyclic compound. Okay, there is a formation of a cyclic beginning between iridium and this ethene molecule. And if you will take alkyne, then there will be a double bond. So this type of reactions is known as oxidative addition reactions, and this mechanism, the way in which this reaction is occurring, is known as concentrated oxidative addition mechanism. Okay. Another mechanism for oxidative addition reactions is Sn2 mechanism. Next one is the Sn2 mechanism. I think everyone is aware with this Sn2 nucleophilic substitution reaction, in which a nucleophile attacks on a molecule, on a polar molecule at the cationic part or electrodeficient part of that species, and leaving group leaves the molecule, and there is the formation of bond between nucleophile and that carbon center at which the nucleophile is attacking. Like if you are nucleophile, and let's say I am taking example of this CH3X, it plus charge, there is a minus charge. If it is an X and any electron withdrawing group, on this will attack here, this leaves, and nucleophile CH3 X minus. Okay, this is the example of Sn2 reaction, where the nucleophile attacks and leaving group simultaneously leaves the molecule. Again, this is a concerted mechanism. Okay, and nucleophile attack from the backside. Okay, you are aware. So in this case also, for the oxidative addition reaction, something happens in the same way. There is a very minute difference between this Sn2 nucleophilic substitution reaction and this Sn2 mechanism of oxidative addition reaction. This Sn2 mechanism occurs when your XY is a electrophilic polar molecule. Example, if you have like Rx, where X is equal to your chlorine, bromine, iodine. It can be methyl iodide, ethyl iodide, and any other halo compound. Okay, so what happens here? I'm again taking the same complex. This is LNM, and let's say we have this X and Y ligand. It has plus charge, let's say partial charge, it has partial minus charge. Then this metal will attack here, and this will leaves, and you will get this LNMX species plus Y minus. Here, if there is an electron in this complex, here also will be the n electron in the complex, and then eventually the addition of this Y minus occurs. Eventually the addition of Y minus occurs, and this complex, it has n plus 2 electrons. Okay, so this type of reactions, or in the Sn2 oxidative addition reactions, this type the reaction proceeds in this way. Okay, and the most studied example of this XY in this Sn2 reaction is methyl iodide. Okay, now I will explain this by taking a real example. Again, taking a Voska complex, and this is over again Voska complex, Cl, PPH3, this is CO, this is PPH3, and let's say I'm treating it with methyl iodide. Okay, and when it will be treated, it will form this complex IR methyl iodide. Will be add methyl here, iodine here, trans to each other, it will be Cl, and it will be PPH3, CO, and PPH3. Okay, if you see here in this complex, methyl and the iodine, they are in trans to each other, whereas in case of this concerted mechanism, both the atoms of the ligand, they were cis to each other. Now why this? Because in Sn2 oxidative addition, the attack is occurring from the backside, and when the reaction occurs, this type of complex is formed. This forms, and then this iodide attacks on this iodine iridium complex. This I minus attacks on this iridium complex and to form this. This is the slow step. This is the fast step. You can again represent in this way, like in the form of tension state that we actually see in that Sn2 nucleic substitution reaction. Here also there can be a formation of a tension state, and that tension state will be like this. Iridium of your OSCA complex. This is your Cl, this is your PPH3, CO, and PPH3. There can be the formation of this type of transition state in this Sn2 reaction. Okay, so these are the two mechanisms by which this oxidative addition reactions occurs commonly. Okay, so now go through this video, and if you have any doubt, you can write in the comment. Okay, good luck.